Okay, this week we will read some about the history of probability, and one of the topics I'd like to focus on in this week is conditional probability. And I have two examples here in this video, the prosecutor's fallacy and medical testing, that really illustrate how important these ideas are. So first, let's just look at the notation for conditional probability. When you see this P parentheses A slash B, this is read the probability of A given B, or the probability of A assuming B happened. And so I have written here, this means the probability that A happens given that B has occurred. The probability of A assuming that B occurred. And you can see that it'll be important to make a distinction. I may turn this around and say the probability of B given A, which means the probability that B happens given that A has occurred. Alright, so first, of course, you need to be real clear about how we calculate a probability. So the basic definition is the probability of an event is the number of ways that the event A can occur divided by the total number of possible outcomes that could occur. And we need to also sometimes think carefully about the fact that these must be equally likely possible outcomes. And of all of the equally likely possible outcomes, how many of those are in the event that we call A? So as really one of the most basic examples, we'll look at roll a single six-sided die. What's the probability of rolling a 5? Okay, so the probability of rolling a 5, I could write like this. Shorthand. It's the probability of the event that we get a 5 when we roll a single six-sided die, a fair die, where all of the sides are equally likely. I have how many total possible possibilities? And the answer is 6 different possibilities, all equally likely. How many of those are in the event that you get a 5? Of course, it's 1. So that's my probability. And I can always write a probability as a fraction. We could also write that as a decimal if you divide. Now if I divide this, I get about 0.16 repeating, so let me just say approximately 0.167, and so we could write it as a decimal like that, where it's not exactly equal. This is rounding off. And then I could also write any decimal I could write as a percentage, so I'll say 16.7%. So all of those are different ways to write the same answer. 1 out of 6, 16%, 0.167. That's the probability of rolling just a 5. Now, what's the probability of rolling a 5 given that the number is odd? What's important to realize is now with this conditional probability, what I would do is I would write this like the probability of getting a 5 given that we have an odd number. That means that you're reducing the number of total possible outcomes to whatever is given. So if you're given that it's an odd, on a six-sided die, 1 through 6, there's the 1, 3, and the 5. That's 3 possibilities. That's 3 total possibilities. How many of those are a 5? Out of the 1, the 3, and the 5, of course, just one of them. So my probability now is 1/3. I don't like the way my fraction is getting connected to the box. Okay, there we go. And then, of course, I can write that as 0.33. It's, again, this is repeating, so in decimal, this is not exact unless I put the bar, and I would say it's about 33%. Those are all different ways of writing that. Okay, so that's the idea of a conditional probability, that I will restrict the total number of outcomes to just those things that are given, and then say out of the things that are given, what's the probability? What's the probability of a specific event? All right, let's move to a little bit more sophisticated kind of question. This is the prosecutor's fallacy. It's a fascinating example. It has many real-life examples through history of the legal system. So here's just an example that I've made up, and we'll have some reading assignments where you'll see some real cases where this occurred. So this says a city contains 2 million people. In that city, one person has committed a crime. The police collect DNA evidence at the scene and find that there are 7 people living in the city that exactly match the evidence found. Prosecutors, in a rush to make a case, select one of the 7 people that match the evidence and charge them with the crime. At the trial, attorneys for both the prosecution and the defense speak in terms of probability, and both use expert testimony involving statistical evidence. The following questions are considered. Number 1, if the person is innocent, what's the probability they match the evidence? And number 2, if the person matches the evidence, what's the probability they're innocent? Okay, well, you can see what I'm doing here. I've posed these 2 questions that almost sound the same, but if you recognize that the topic is conditional probability, you see that I've changed what those conditions are. Like, if the person's innocent, what's the probability of matching the evidence? And if the person matches the evidence, what's the probability they're innocent? Are a different conditional probability. This is essentially saying, given the person is innocent, what is the chance that they match the evidence? And this one says, given the person matches the evidence, what's the probability that they're innocent? Okay, so the way I'd like to solve that problem is to create a table. Now, there's different ways I could do this with probability trees. I can use Bayes' theorem. I can use a very sophisticated formula called Bayes' formula to answer this. But with the information that's given here, it's possible for me to just create a table to answer this in a very straightforward, simple way. It doesn't require formulas, doesn't require a lot of sophisticated math, because there's enough information here in this example, the way that I set it up, to answer it. So let's do that. What we're going to do is create a table. And I'm going to write across the top, I'm going to say there are 2 possibilities. The person's guilty and then not guilty. And then there's 2 other possibilities, which is they match the evidence. Or they don't match the evidence. Now in this table I'm going to create a column for totals here and another row for totals down here. Now, the first place that we could start was that there were 2 million people in the city. So let me put that as a total down here. 2 million. Another thing that we were given is that was one person that matched, that was one person that committed the crime. One person that's guilty. Now, that person that's guilty was among the 7 people that matched the evidence, so I'll include them here, that they're guilty and they match the evidence. And you can realize that each of these boxes represents a sort of combination of both conditions. Now, you remember that there were 7 people that matched the evidence, and only one of them was actually guilty. And so I'm going to say there are 6 people that were not guilty and matched that evidence. Now, that can happen actually even with DNA evidence, because what generally happens is that the forensic scientists will sample the DNA. They take a sample of DNA from suspects, and they take a sample of DNA from the crime scene, and they match it. And so they don't necessarily analyze every single strand of the entire DNA. It's not the same thing as a complete sequence of the DNA. It's a sampling of parts of the DNA, and so it is possible that you could have several different people that are not even related. It's theoretically, statistically possible. And so you don't put somebody on trial simply by the DNA evidence only. You'd have to have motives, and they have to be, perhaps they were at the scene of the crime, or there's evidence, other kinds of evidence. You build a case and you include DNA evidence, but you're not going to convict somebody simply only on the DNA evidence. Now, I've created this question where that's essentially what's happening because I want to emphasize the prosecutor's fallacy, and in order for that to occur, I need to build the problem in this way. Nobody would really be put on trial only because of the DNA evidence, only because they're one of 7 people, naturally, right? But suppose that this is somehow this situation I'm creating is sort of exaggerating a real life situation to make it real clear where the fallacy occurs, right? So anyway, back to this example, we had 7 people that matched the evidence. Now, if you realize that there were 2 million people total, how many people don't match the evidence? There were 7 people that do match the evidence. The rest of the population doesn't match the evidence. So that's going to be 1,999,000. Let's see if I can do the subtraction here in my head. 993, right? If I add those together, 7 more people, and you've got 2 million total. Okay. Now, it's set up in that problem that we had only one person that was guilty. So there are no people that are guilty and don't match the evidence. There wasn't such a person as stated in the question. So let's put a 0 there, and so I can put a total here for 1. One person that's guilty total. Now, what could I do here? Well, if I can also look at this row, and if I have the total number of people that that don't match the evidence, and I have how many of them are not guilty, I guess you could say, or if you have none of them are guilty, the rest of them have to be not guilty. In other words, you could say these two numbers together have to equal 1,999,993, just like the 1 and the 6 make 7. So this is a very easy arithmetic here. I can just copy that number, 1,999,993. 0 people that are guilty and don't match the evidence, plus 1,999,993 people that are not guilty and don't match the evidence. Together, that adds up to all the people that don't match the evidence. Okay, well then I can add these numbers as well, and of course if you add 1,999,993 plus 6, you get 1,999,999, and naturally that's going to be exactly the number that when you add these two on the bottom cells here in this table, 1 plus the 1,999,999 people that are not guilty, that adds up to the 2 million total, right? One person guilty, everybody else not guilty. You could also check, it makes sense that this number should be as it is because if you look at the total number of people that are not guilty, 6 of them match the evidence. The rest of them don't match the evidence. All right, now that I've completed the table, I can go back and look at those questions that were posed. So let me write them down. Let's see if I can fit this all on the screen at one time. What I'd like to do is I'd like to answer question number 1. Let me look at it again. What was the first question? If this person is innocent, what's the probability they match the evidence? So that is, if they're innocent, that's the given, and that goes after the straight line that we create to indicate the condition. So we'll say, what's the probability of the particular evidence given the person is innocent? And in order to answer that, what I will do is I will look at what's the total number of people that are innocent. I'm going to take innocent to mean the same, of course, as not guilty. What's the total number of people that are not guilty? The total number of people that are not guilty is 1,999,999. It's the bottom of this column, right? The total number of people that are innocent. 1,999,999. 999,999. What I'm thinking here is not, of the people that match the evidence, what's the chance that they match the evidence? I'm talking about of the people that are innocent out of the entire population, sort of, if the person is innocent, what is the chance of actually matching the evidence, right? Not if they're innocent and match the evidence, what's the chance that they match the evidence? In other words, if you were in fact truly innocent, you had nothing to do with it, you could be any one of the people in the city, and we're asking of all of the people in the city, of all the people that were innocent, that had nothing to do with it, what is the chance of anybody particular matching the evidence? Right? So under the assumption, only assuming that you're innocent, what would be the chance that you match the evidence? It wouldn't make any sense to say if you're innocent and you match the evidence, what is the chance that you match the evidence? Of course, if you are one of the 7 people that match the evidence, then it's 100% chance that you match the evidence, right? You have to realize that when I say if the person's innocent, I'm talking about have nothing to do with it. So, and from the entire population of the city. So the total number of people that are not guilty, the total number of people that are innocent, how many of those match the evidence? 6. And so we'll divide 6 divided by 1,999,999. So let's see, 6 divided by 1,999,999. The calculator comes up with an answer of, you might see it 3 times 10 to the negative 6. Because you might see it that way, if you did this, I'll write it that way. That's scientific notation, of course, and that means I'm going to move the decimal 6 places to the left, which means I need to put 5 zeros. 1, 2, 3, 4, 5 zeros, and a 3. Right? And then if you were to put that as a percentage, if you were writing that decimal number as a percent, you could move the decimal over 2 and say 3 zeros and then a 3%. Okay, so 3/10,000ths of a percent. 3/10,000ths of a percent that if somebody is innocent that they match the evidence. So this makes the person look guilty, actually, because what you're saying is that what this question is doing is saying that if you're innocent, the chance of you matching the evidence is incredibly small. So it's not likely. It makes it look like very unlikely, very small chance that somebody would actually match the evidence, and therefore they look guilty. Right? This makes the person look guilty. I would say because the probability of the evidence is so small. It's difficult to believe it could happen, right? And yet, of course, here's somebody who does match the evidence. So this would be something that the prosecutor would use. They would say, if you are innocent, you say that you're innocent. Suppose that you were. Well, if you were innocent, the chances of this happening, of you matching the evidence, is so small that it's just very unlikely that it would happen. It's difficult to believe that you would match the evidence. And yet here you do match the evidence. And so that links you to the crime. It makes you look guilty because you have a connection to the crime. If you were innocent, the chance of your matching the evidence is so small that I don't believe that it could even happen, right? It's 3/10,000ths of a percent that you would match the evidence. And so this is building a case to make the person look guilty. Okay. Let me take that same table now and look at the other question. So I've tried to move things around right here and shrink down my table in size so that you could see everything and look at both of these questions right next to each other, because the whole thing that I want to get across is the difference between question number 1 and question number 2. Right? Question number 1 was, what's the probability of the evidence if the person is innocent? And you can see that all I have to do and answer that is look at what's the total number of people that are innocent and how many of those match the evidence. And so of the people that are innocent, how many match the evidence means that I'll reduce my total number of possibilities to all the people that are innocent, and out of those, how many match the evidence? There were 6 people that matched the evidence out of all of the people that were innocent. And so the probability that you match the evidence, if you are in fact innocent, is about 0.3%. Very, very small. And of course that makes the person look guilty, because the person actually does match the evidence, and the chance that they match the evidence is so small that we think it's unlikely. And so now compare that with question number 2, which is, what's the chance that the person is innocent if they match the evidence? All right, well now if I say you match the evidence, the person does match the evidence. Of all the people that match the evidence, how many are those? How many are there that match the evidence? The total number of possibilities, there's 7 people that match the evidence. So out of the 7 people that match the evidence, how many of those are innocent, right? What's the chance of innocent assuming matching evidence? Well, assuming you match the evidence means I'll limit the total to just the people that match the evidence, which is these 7 people. And out of those, how many are innocent? 6. So if we do 6 divided by 7, what do you get there? 6 divided by 7, it's about 0.857. Let's say 0.857. Now this is a very different number. And as a percentage, that's 85.7%. Now that's completely different. Turn things around. This would be what the defense would say. The defense would say you simply can't take one person out of 7 and charge them simply by the DNA evidence. Because look, you had 7 people and only one of them actually did it. That's already established. And if only one of them did it, and you pick one person out of 7, there's a 6 out of 7 chance that the person that you picked is innocent, right? There's an 85% chance that the person is completely innocent, had nothing to do with it, because there were 7 people that matched the evidence. Only one of them committed the crime. Now this completely changes the perspective on this case. I mean, of course, you can already see that. You already realize that the way that I set up the problem. But imagine the defense coming in and saying, if the person matches the evidence, there's just not enough statistical evidence to suggest that you should convict, because there's a very high probability, there's an 85% chance that the person is completely innocent, because we had 7 people that matched the evidence, right? 6 of them are completely innocent. So there's an 85% chance that we've got somebody here who is completely innocent, even though they match the evidence. And so it would have been question number 1 that the prosecution would try to pull a fast one, right? They would try to trick the jury, or they may even be tricking themselves. The prosecution may not even realize what they're doing. You know, if the situation was more complicated, if it was more realistic, the prosecution could be thinking, if the person is innocent, all of the evidence that we've collected makes this so unlikely that it would occur that we don't believe that they're innocent anymore. We believe they're guilty, because the chances of all of this particular evidence, all the DNA evidence we've collected, the chances of them matching is so small that we don't believe they're innocent. And therefore, we have built a case, right? And that sounds completely plausible. That's very seems like a perfectly routine part of a prosecution. So what I'm suggesting is it would not be enough evidence. There wouldn't be enough statistical evidence if you had 7 people that match the evidence. And when you look at it that way, you say, okay, right, of course. If you had 7 people that match the evidence, you can't just pick one at random. Right? And so that's what the defense would do. They would say, if there was a good defense attorney, would come in and say, well, this is absolutely ridiculous. If you match the evidence, the chance that you're innocent is 85%, case dismissed. Right? So this is, so when people talk about the prosecutor's fallacy, when you read about the prosecutor's fallacy, the prosecutor's fallacy is really, I would say, basically making a confusion about these two. The prosecution would use the first probability to make the person look guilty, and that's why it's called the prosecutor's fallacy. And what really matters to the jury is that if you have the evidence, if you have some evidence against this person, and you say, well, given this particular evidence, what is the chance the person is innocent? And it's really the second question that the defense would argue toward, and really the one that the jury should take into account. So I would say that first probability really isn't the first one really should not be the only piece of it should not be the entire basis of the prosecution. The prosecution would actually have to have other things besides just the statistics and the data that I've given. They'd have to have perhaps other kinds of things that connected the person to the crime. Not that they're one out of seven people that match the evidence. They'd have to not only that, but maybe they have all of the cash in the freezer, or maybe they have there's physical evidence of the crime in their basement, a skeleton in the closet, something like that, or they have some clear motive, or other things that the prosecution would use in addition to the fact that they match the DNA evidence. Then you've got a strong case. Okay, that's the prosecutor's fallacy. And I have one other example that I want to show you, which is this issue of medical testing. It says a certain disease affects 1 out of 1,000 people, and a medical test is developed that is 99% accurate in identifying those that have the disease and those that do not. That is, if a person does have the disease, the probability the person will test positive is 99%. And further, if a person doesn't have the disease, the probability the person will test negative for the disease is also 99%. Now imagine the company develops the test. They also produce a very effective advertising campaign. And of course, an advertising campaign that's going to be effective would skip all those numbers and appeal to people in some other sort of emotional way. And out of the millions of people who see these ads, let's suppose that 100,000 people take the test to determine if they have this disease. The following questions occur in discussions between patient and doctor. Question number 1, if a person has the disease, what is the probability they test positive? Question number 2, if a person tests positive, what's the probability they have the disease? Wouldn't that be the most interesting, the most important question there? Number 2, if you test positive now, what's the probability that you do have the disease? Okay, so let's look at both of those. And again, this is an example where I could use Bayes' formula. I could approach this with sophisticated techniques. In general, you would need to. However, because of the way that I've stated the problem and a few assumptions I'm going to make as I start this, we don't need a formula. We're going to create a table just like before. I'll be able to answer this because I do have enough information in this example to answer these questions. If the question became perhaps more and more realistic, we would need a more sophisticated method. Bayes' formula that I mentioned a couple of times, I hope that you're going to read a little bit about, would be something that would be useful when you try to determine conditional probabilities, and perhaps there might be less information that's available that I have, or the information is stated in some ways that you wouldn't be able to do it the way I'm going to do it. All right. So anyway, let's try this one. So the disease affects 1 out of 1,000 people. So I've got again, I've got this sort of two conditions. Either you have the disease or you don't. You test positive or you don't. And so that makes it easy for me to make a table. So let's say somebody has the disease and then no disease. And then I'm going to need totals. And then I'm going to say you test positive or you test negative. And I'm going to create some totals as well. And Okay, so here's my table. Let's see if we can put some numbers in here. We had originally in the question that the disease affects, is that with an A or an E? I don't know. I think it's actually an A. Affects 1 in 1,000 people. But let's suppose that 100,000 people actually take the test. So if it's 1 out of every 1,000 and then you have 100,000 take the test, that would be the same ratio as 100 in 100,000, because I'm just going to multiply both of these by 100. Right? And so it'll affect 100 people in 100,000. Now that isn't necessarily exactly always true, but I'm going to make that assumption here so that I can build a table as an example with some specific concrete numbers. If you didn't have those numbers, if you didn't make that assumption, you could use Bayes' formula to get a more realistic answer here. But if the numbers were, if we really knew, and as an example, that we had 100,000, let's just take as an example that there really were 100 people that had the disease. Right? If you had 100,000 and take the test, and let's suppose that we knew that there were 100 people that actually had the disease. And then I'm going to build a table based on that assumption. And then I can do this with a table, and I don't need to use Bayes' formula. All right, so enough of that. Let's now use everything else that the question said. So if there were 100 people that have the disease, the rest of the people don't have the disease, that's just subtraction. 100,000 take away 100. I'll have 99,900 without the disease. Now the test, it said that it was 99% accurate. Let's suppose, for the purpose of having concrete numbers, that there were actually going to be 99 people that actually test positive, since it was 99% accurate. So then we have some concrete numbers again. So if there were 99 people that tested positive out of the 100, that would be an expected result from if there were 100 people with the disease. Right? 99 of them, if it was 99% accurate, 99 of them would test positive, and the test would miss one person. They have the disease, but the test was only 99% accurate. And out of 100 people, it shows 99 have the disease, and it misses one. So this is a false negative. Now it was 99% accurate as well in identifying the people that don't have the disease. 99% of the time, it'll show up negative, right? So what I need to do is figure out what's 99% of this huge population. There's 99,900 people with no disease, and 99% of them are going to come out negative. The problem is that's going to be a big number, right? It's 0.99 times 99,900, and I get 98,000 people. That's 99%, 98,901. I just multiplied 0.99 times 99,900, and I get this 98,901, which I'm putting here because that's 99% of the people that don't have the disease. 99% of them are going to come out testing negative, which is most of them, right? But the problem is that actually there's how many is that? I need to subtract. It's hard to, I should be able to do that in my head, but that's just too many nines. Okay, so let's do 99,000. I'll take the number on the bottom. 99,900 people minus 98,901, and I got 999 people that are actually coming out positive even when they don't have the disease. Right? Look at that. Add these two together and you get the total number of people without the disease. The way that I built these numbers, the way that it's split is that this is 99%, and of course that would be 1%. Now I could have done that one in my head, right? I could have gotten 1% would mean move the decimal over 2 places to get 1%. So 999 people. 999 people, there's so many nines, are testing positive and don't have the disease. Those are false positives, right? Maybe it's nice to write that down just because that's a familiar sounding term. False positive. It's right there. This is the false positive and this was the false negative. because they're wrong, right? They're coming out positive, but these people don't have the disease. And why would that happen? Why would you have so many people coming out positive that don't have the disease? Because you had so many people that didn't have it, right? They were only affecting 1 in 1,000 people. And when you've got so many people, even when they don't have the disease, 1% of that population is still going to come out testing positive. And there they are. That's 1% of that huge population. 999 people getting false positives. The rest of them, most of them, getting the correct result that they're negative when they don't have the disease. Okay. Well, let's do the totals then over here. 99 plus 999. Would that be, could I do that in my head? That's 1,098. And then if I added these two together, I think I can do that one in my head, 98,902. And then let me just check. If I do 1098 plus 98,902, it better come out to 100,000. That's what I want. Good. All right. Okay, so let's look at those questions that could come up when the patient is talking with the doctor. So back to the question. Number one, if a person has the disease, what's the probability they test positive? So I've stated my conditional probabilities. Let me make this smaller again. Okay, so I have stated again my conditional probability in terms of if. And it's the if that's the part that's given, right? So the question was, if a person has the disease, what's the probability they test positive? So if they have the disease is given that they have the disease, and it's the given that goes after that vertical bar. So the question here is, what's the chance you test positive if you have the disease? And the way to understand that, the nice thing about the table is that we could look at a row or a column and take that row or column as the given. So if the given is that they have the disease, all the people in this column here have the disease. There's a total of 100 people. And so in this case, with these numbers, I can say that there were 100 people with the disease. And how many of those test positive? The number that have the disease and test positive is this number right here, 99. There's 99 people out of 100 that test positive. Out of the 100 people that have the disease, of course, that's 0.99, and that's 99%. This is no surprise at all. It's exactly what was given in the question, that the test is 99% accurate. If you have the disease, 99% of the time, it will show a positive, and that's exactly what we get. However, it's really important to realize, and as you learn conditional probability, you begin to realize that if you just change those, it could be completely different, just like it was in the case of the prosecutor's fallacy. The question that I want to ask now is that what if you test positive? What's the chance you have the disease? And just like in the prosecutor's fallacy, it's the second one that actually is the one that really would matter, right? I mean, I'd like to know that the test is 99% positive. But what I really care about is if I tested positive, now what does that mean? So what is the probability you have the disease given that you tested positive, right? If you test positive. Well, I will say if you look at the total number of people that test positive, you're saying if you tested positive, what's the chance of having the disease? Well, we'll look at, in this case, how many people actually tested positive. There were 1,098, the total number of people that tested positive. So I'll put that on the bottom. That's the total number of possibilities in a particular example, right? In a particular case of 100,000 people, suppose that we had 100,000 people and 100 of them have the disease and 99 of them test positive, and like we went through, there were 99,900 that didn't have the disease, but there were so many false positives because there were 1% of those that will still test positive, right? Even though they didn't have the disease. And 1% in this case was a big number. Put those two together. 99 plus 999, 1,098 people that tested positive total. Well, how many of those actually had the disease? Actually, it was a small percentage, 99. 99 out of 1,000. If you actually divide 99 divided by, it's not exactly 1,000, it's 1,098, so 1098. If I do that, it's about 0.09. And if I round off, I'll say just 0.09. And so that's about 9%. That is completely different. I mean, dramatically different. If you test positive, the chance that you have the disease is only 9%. So that would be a relief, right? To realize that, oh, there's only a 9% chance you have the disease. Well, how could that even happen? Well, what's happening is that we have way too many false positives in this situation. So you wouldn't really want to have 100,000 people necessarily take this test, or even if they did, maybe you'd have to have something else. Just like in the prosecutor's fallacy, you'd have to have something else besides just the statistics. You'd have to say, well, not only did the test come out positive, but you have the symptoms. And we have perhaps other things that indicate you have the genetics, you have the history, family members, perhaps other things that would point to that you really have the disease. So you would just include this in the entire analysis, right? So, so the point is how significant the difference is, right? And I want to get across the difference and the importance of understanding conditional probability. On the one hand, the first question, if you have the disease, what's the chance you test positive? The answer was 99%. Compare that with the question that says, well, if you do test positive, what's the chance that you actually have the disease? It could be very small, right? In this case, I came up with an answer of 9%. And so that was because we have no other reason to indicate that this person has the disease, only the fact that they tested positive. And when you have so many people taking the exam, taking this medical test, and so many false positives in this particular example, you could be one of those false positives. You could be positive, and it could be not really a case that you have. You could be among this group that doesn't have the disease. And so the actual number that has the disease is small compared to the number of false positives. So important difference. Both of these examples make me think of one time teaching this material in a course in probability, and a student saying, we were talking about probability of dice, or cards, and the student says, well, I'm going to be a gym teacher. Why do I care about this stuff? Why do I need this stuff? And both of these are my answer to that question. You may be called to be on a jury. Perhaps you may go through some tests, some medical tests, and both of these are illustrating how important it is to be educated. And imagine that the more our society was better educated about these ideas, how much better it would be in general. So, okay, so that's it. Those are my two examples. Hope that was helpful.